sometimes you can use a few terms of a series to get a sense of where the series is going. Right? So if by listing out maybe like one or two terms of the series, getting that sum, I'm not going to be too far off of the correct sum. Then it would beg the question of like, well, how much calculus would I really need to do? You know, do I actually have to use some advanced technique to find the real sum? If by listing out, let's say, the first three terms of the series, if I'm able to come within like 1/10,000th of the correct answer, then is that a close enough approximation? And the answer depends on what you're willing to accept in terms of an approximation, the amount of deviation. So that's where this relationship comes into play. So the remainder is equal to S minus S sub n. All right, so we'll talk about that for a second here. And it's really more so kind of where that comes from. The idea that the sum itself, the sum of the series would be, if you were to go out some number of units, you'd get the sum for that number of units. All right, so in the case of the first example, it's saying by using 6 terms. So what it's telling us to do is find S sub 6, which would be the same as this summation going from 1 to 6. All right, and so that's not going to be the exact answer. That's not going to be the exact sum. There's going to be some amount of error associated with that. Oh, crikey. Okay, so we know that the S sub n, just going out 6 terms, is not going to get us the precise answer, but it could get us close. All right, so what I want to know is how far off we're going to be. So that's what the R sub n represents, the amount of error. But the R actually stands for remainder, but we call it the amount of error. All right, so you solve it for R sub n and you get this relationship. All right. So if we were to use the integral test, under normal circumstances, what I would do would be to take this guy here, find the antiderivative from 1 to infinity of the equivalent function 1 over x to the 4th dx. That would be the integral test to determine if it converged or diverged. All right. So what I want to do here is list out the first 4 terms of the summation. So 1 over 1 to the 4th plus 1 over 2 to the 4th, 3 to the 4th, 4 to the 4th, 5 to the 4th, 1 over 6 to the 4th. That is a poor quality 4, and it needs to change. All right. So this will be an approximation. We would also have the rest of the way, because if I were to find the sum of this series, like I said, I would go from 1 to infinity. But by doing this calculation, we've already kind of been spotted the first 6 calculations. So if I were to use the integral test, I wouldn't need to go from 1 to infinity. I just need to go to the rest of the way. All right, so I would need to go and start at the 6th value and go to infinity. So that's what my R sub n would be. It would be the sum from 6 to infinity of 1 over x to the 4th dx. All right, the idea being that if I have any degree of accuracy through this calculation, then this R sub n should be very small. All right, because if it's very small, what it means is that I got most of the way to the correct answer just by doing the calculations for the first 6 terms. Everything else, if it's negligible, it means that I can use the first 6 terms as an approximation for the series, a reasonable approximation. All right, so How do we do it? Well, we certainly don't just add it by hand, right? That's not going to be fun. All right, so alpha window, option 2. Choose a variable, doesn't matter. I like I. From 1 to 6. And it would be, for me, it would be 1 over I to the 4th. Math bracket, if it math fracts, it doesn't, at least not easily. All right, so it's going to be about 1.0811, roughly, which I guess is what about means. 1.0811, roughly. I mean, it should be because it's made up of fractions, but it gets so tiny in terms of the denominators that the calculator's having a hard time with it. What you can do is you can do it a piece at a time. If you do that, then the calculator might handle it, account for the numerator only, then the denominator, and see where you go from there. But just because it won't math fract doesn't mean you did anything wrong. All right, now the other one, we need to clean this up a little bit. And the cleaning up happens when we apply the technique for the improper integration. So limit as a approaches infinity, going from 6 to a. X to the negative 4th is the way I prefer to write it, dx. Integrate, you're going to get new exponent negative 3, divide by that, so negative 1/3 x to the negative 3rd on the interval of 6 to a. Still looking for the limit as a goes out to infinity. All right. Cleaning it up, we're looking at negative 1/3 a to the negative 3rd minus a negative, so plus 1/3 6 to the negative 3rd. All right. Whether you write it as a negative exponent or you write it in fraction form, it's not going to make a difference. This is going to 0. This is a constant. The limit of a constant is the constant. So that 1/3 times 6 to the 3rd power, that's the amount of error. So that's 1 over 216 times 3, was that 648? All right. So the R sub n value is the amount of error, like I said. And that error represents how far off your answer is from the real answer. But again, the real answer is related to the function approximation. So if that in and of itself has a smidge of area to begin with, because one is a smooth, continuous function, the other is made up of discrete points. All right. But what this is saying is that the 1.0811 would only be off by approximately 1 over 648. Right? I mean, that's not even a percent. So not much variation between what we got just by going out 6 terms and what the correct answer ought to be around. All right? And you could kind of verify it. Just put in something really large for your summation in your calculator and just find the difference between the two. All right? So instead of 1 to 6, I'll do 1 to like 60. That might be too much. I'll do like 1 to 20. 20 is pretty safe. Not 120. I'll do 20 up here. See where it goes. All right. So the difference between the two, I mean, we could just do the subtraction, but it looks like it's roughly 0.0011. 6, but I'll just type it in. All right, and 1 out of 648. It's not too far off from that. Right, so it's in the same neighborhood. So it gives you a pretty good sense on the calculator. So what they again were looking for was the approximation, which is the 1.0811, and then an estimate for the maximum error, which would be 1 over 648. Question?
Seeing another example like this, can I just do integrals, like 1 to 8, whatever that I'm looking with the parameter, and bring two different integrals?
So an integral for this part?
Yeah.
You'd have to, it would only be the one integral for the remainder. This part, the sum approximation is specifically telling you to use 6 terms.
Yeah, that's what I'm saying. I can do this with integration 1 to 7.1 into 6.7 term, and the other one integration from 6 to infinity.
You cannot do the integral from 1 to the 6th term because you're finding the sum by using 6 particular terms. That's discrete data points, not continuous. If you use an integral, you're basically overestimating because you're accounting for all of the function that exists between points. What this theorem is calling for is just the values at the particular point.